Max Planck, a name forever etched in the annals of physics, was a figure who transcended the norms of scientific thought and perception. Born in 1858 inches, Kiel, Germany, his journey to becoming one of the most significant figures in the history of science is nothing short of extraordinary. From his early academic pursuits to his monumental contributions in the field of theoretical physics, Planck's work has had a lasting and transformative impact. To understand the profound legacy of Max Planck, one must first grasp the essence of his early life and the formative experiences that shaped his thinking. Max Planck was born into an academic family, which set the stage for his later career. His father, Johann Julius Wilhelm Planck, was a professor of law, and his grandfather, a well-known historian. From a young age, Planck was encouraged to pursue intellectual endeavors, and his early exposure to the world of academia instilled in him a deep respect for knowledge. Initially, he displayed a keen interest in music, but as he grew older, his attention turned towards the mysteries of the natural world. He attended the University of Munich and later the University of Berlin, where he studied physics under some of the most brilliant minds of the time. As a student, Planck was particularly drawn to the works of renowned physicists such as Hermann von Helmholtz and Gustav Kirchhoff, who were pioneers in the fields of thermodynamics and radiation. These influences would leave an indelible mark on his thinking and set him on a path that would challenge the conventional wisdom of the scientific community. Planck's early academic career was marked by an intense focus on thermodynamics, a field that was growing rapidly at the time. However, his pursuit of knowledge was not just about mastering existing theories, it was about pushing the boundaries of understanding, seeking answers to questions that had eluded scientists for centuries. It was in the late 19th century that Planck began to make significant strides in his work. The field of thermodynamics had made enormous progress, but there was one issue that no one had been able to fully explain: blackbody radiation. Scientists knew that heated objects emitted radiation, but the exact nature of this radiation and how it related to temperature was a puzzle. Classical physics, which was grounded in the principles of mechanics and electromagnetism, struggled to provide an adequate explanation. Planck, with his background in thermodynamics, approached the problem from a different angle. He sought to explain the distribution of radiation emitted by black bodies, idealized objects that absorb all incoming light and radiate energy. Classical theories, based on the principles of electromagnetism, predicted that as an object's temperature increased, the amount of radiation emitted would increase without bound, leading to what was known as the ultraviolet catastrophe. This theoretical outcome contradicted experimental data, which showed that the radiation from heated objects did not increase infinitely. It was at this juncture that Planck, in 1900, introduced his revolutionary idea: energy could only be emitted or absorbed in discrete quantities, or quanta. This was a radical departure from the continuous models of classical physics, which assumed that energy could take any value. Planck proposed that the energy of oscillators within a material was quantized and could only take on discrete values that were integral multiples of a fundamental unit. This fundamental unit, later known as the Planck constant, was central to his theory and represented a profound shift in the understanding of energy and matter. Planck's introduction of quanta was initially met with resistance. It was such a radical idea that it was difficult for many of his contemporaries to accept. However, Planck's mathematical formulation was so accurate in explaining the observed data that over time it became clear that his theory was not only plausible but also essential for a deeper understanding of the physical world. Planck's work laid the groundwork for the development of quantum mechanics, a field that would soon revolutionize not just physics but all of science. Despite the initial skepticism, Planck's theory gained traction. He was soon recognized for his contributions to science, and his name became synonymous with the emerging field of quantum theory. His work on blackbody radiation and the quantization of energy opened the door to new ways of thinking about matter and energy. The implications of his discovery went far beyond the confines of thermodynamics. They extended to the very foundation of physics itself. In many ways, Max Planck was ahead of his time. His ideas challenged the deeply entrenched principles of classical physics, and they provided a framework for future generations of scientists to explore the unknown. In the years that followed, his theory was expanded and refined by other physicists, including Albert Einstein, Niels Bohr, and Werner Heisenberg. Einstein's work on the photoelectric effect, for instance, built upon Planck's theory of quanta, and provided further evidence of the quantization of energy. Bohr's model of the atom, which introduced the idea of discrete energy levels, was another extension of Planck's quantum theory. As the 20th century unfolded, the field of quantum mechanics became the dominant paradigm in physics. Planck's contributions were pivotal in this transformation. Yet, despite his profound impact on science, Planck remained a humble figure. He never sought fame or recognition for his work, and he continued to explore the mysteries of the universe with the same passion and curiosity that had characterized his early years as a student. Planck's life was not without its challenges. During the rise of the Nazi regime in Germany, Planck found himself in a difficult position. As a scientist, he was committed to the pursuit of knowledge, but the political climate of the time was oppressive and hostile to many of his colleagues, particularly those of Jewish descent. Planck was deeply saddened by the departure of some of the brightest minds in physics, including Albert Einstein, who left Germany for the United States. Despite the political turmoil, Planck continued to work and maintain his integrity as a scientist, even as his country descended into the horrors of World War II. In the aftermath of the war, Planck's work was further celebrated as a foundation for the future of physics. The Nobel Prize in Physics, awarded to him in 1918, was a recognition of his lasting impact on the field. Yet, even with all the accolades and honors, Planck remained deeply committed to his scientific principles. He continued to contribute to the development of quantum theory, influencing generations of physicists who would follow in his footsteps. Max Planck's story is one of perseverance, intellectual curiosity, and a relentless pursuit of truth. His contributions to science have had an enduring legacy, influencing everything from the development of technology to our understanding of the universe at its most fundamental level. In a sense, Planck's work represents a breaking of the boundaries of human knowledge, opening the doors to an entirely new world of discovery. The field of quantum mechanics, which began with Planck's revolutionary insights, continues to shape the world we live in today, from the development of cutting-edge technologies to the ongoing quest to understand the nature of reality itself. As we look back on the life and legacy of Max Planck, it becomes clear that he was not just a man who broke physics forever. He was a man who redefined what was possible. His contributions to science will continue to inspire generations of thinkers, innovators, and explorers who will build upon his work and seek to unravel the mysteries of the universe. In the world of physics, Max Planck's name will forever be synonymous with groundbreaking ideas, a dedication to discovery, and a legacy that transcends time itself. Max Planck's groundbreaking work in the field of physics is, without question, one of the most revolutionary contributions to science in the 20th century. While his theories may have initially appeared counterintuitive and controversial, they eventually became the bedrock upon which modern physics would stand. In the world of scientific discovery, there are moments that change everything. Planck's quantum theory is one such moment, a moment that forever altered the course of human understanding. While many scientific breakthroughs are the result of years, if not centuries, of gradual progress, Planck's work on blackbody radiation represents a sudden and sharp departure from traditional thinking. This shift was not just incremental, it was transformative. Before Planck, physics had been dominated by classical mechanics, which assumed that energy was continuous, flowing seamlessly from one form to another. This classical understanding had worked well for macroscopic phenomena, but it failed to explain certain phenomena at the atomic and molecular scale, particularly when it came to radiation emitted by hot objects. In his quest to solve the problem of blackbody radiation, Planck began to tackle the deep issues plaguing the existing theories. Classical physics predicted that an idealized black body, a theoretical object that absorbs all radiation, would emit an infinite amount of energy as its temperature increased. This was known as the ultraviolet catastrophe, a paradox that made no sense when compared with actual experiments. The ultraviolet catastrophe was a significant dilemma because it directly contradicted empirical observations, which showed that the emitted radiation from heated objects did not increase infinitely. Planck's insight came when he made an audacious leap. What if the energy emitted by matter was not continuous, but instead came in small, discrete units? Planck introduced the idea of quanta, the idea that energy was not continuous, but instead came in specific, indivisible packets. This was a revolutionary proposal because it turned the classical idea of energy being a smooth, continuous flow on its head. Planck's theory posited that energy could only be exchanged in certain quantities, which he calculated using a fundamental constant known as the Planck constant. The formula he developed to describe the behavior of radiation from a black body was accurate and aligned perfectly with experimental results. It was this very proposal, the quantization of energy, that marked the beginning of quantum mechanics, a field that would go on to transform not just physics, but every aspect of modern science. Before Planck, the world of atoms and subatomic particles was a mystery, a place that science could not fully comprehend. After Planck, that world became a new frontier for exploration. His work provided a mathematical framework for understanding how atoms and particles behave, and it opened up a path for future scientists to explore phenomena that were once beyond reach. The immediate impact of Planck's discovery was profound, though it took some time for the full implications of his work to be recognized. Initially, Planck himself viewed his theory as a temporary fix, a way to solve a problem in blackbody radiation. He did not yet fully grasp the revolutionary consequences of his ideas, but as time went on, it became clear that Planck had unlocked a new realm of possibilities in physics. Other physicists quickly realized that Planck's insights into energy quantization could explain phenomena that classical physics simply could not. This included the behavior of light as both a particle and a wave, which would later be demonstrated by Albert Einstein in his explanation of the photoelectric effect. Although Planck's work was pivotal in the development of quantum theory, it was his willingness to accept the implications of his own discoveries that set him apart. In the early 20th century, many physicists still clung to the principles of classical mechanics, and the idea that energy could only be emitted or absorbed in discrete packets seemed almost sacrilegious. Planck himself initially resisted the idea that his theory would require such a radical change in thinking. But over time, he came to accept the fact that the universe at its most fundamental level operated in ways that were not only different from classical assumptions, but also far more complex and mysterious. One of the key aspects of Planck's personality and intellectual journey was his modesty and humility in the face of his own success. While he could have easily basked in the glory of his scientific achievements, Planck was not one to take sole credit for the success of quantum theory. He acknowledged the contributions of other scientists who extended and built upon his work. For instance, Albert Einstein, who developed the theory of the photoelectric effect, expanded on Planck's quantum hypothesis, showing that light behaved as both a particle and a wave. Niels Bohr, another giant in the field of quantum mechanics, also built on Planck's ideas, using them to create the Bohr model of the atom, which revolutionized our understanding of atomic structure. Beyond the laboratory, Planck's influence extended to the broader scientific community. His work provided a foundation for one of the most important paradigms of modern physics, the probabilistic nature of quantum mechanics. The advent of quantum theory challenged the deterministic view of the universe that had prevailed for centuries. In classical mechanics, the future could, in theory, be predicted with complete certainty given the initial conditions of a system. But in the quantum world, uncertainty and probability became central principles. This shift to probabilistic thinking in the quantum world was famously captured by the uncertainty principle articulated by Werner Heisenberg, another key figure in the development of quantum mechanics. Planck's influence also extended to the philosophical implications of science. His work on quantum theory raised deep questions about the nature of reality and our ability to truly know the universe. The concept that energy could only exist in discrete units called into question the classical idea of a continuous universe, leading to debates about the very nature of reality itself. For centuries, the universe had been understood as a vast machine governed by predictable laws, but quantum theory introduced a level of unpredictability and uncertainty that made many physicists rethink the way they understood the nature of existence. Despite the challenges and controversies surrounding his work, Planck's contributions were ultimately recognized and celebrated. In 1918, he was awarded the Nobel Prize in Physics for his discovery of energy quanta, and his legacy has continued to shape the course of physics for more than a century. Today, Max Planck is remembered not just as the father of quantum theory, but as a pioneer who revolutionized our understanding of the universe at its most fundamental level. His theories remain central to fields as diverse as quantum computing, molecular biology, and cosmology. The very technologies we use today, from computers to medical imaging, owe their existence to the foundations laid by Planck and his contemporaries. In the grand tapestry of scientific discovery, few have had as lasting and transformative an impact as Max Planck. His willingness to challenge the established norms, his insight into the fundamental nature of energy, and his ability to inspire future generations of scientists have made him one of the most influential physicists in history. His work did not just break physics, it broke the very limits of human understanding, opening up new realms of discovery and pushing the boundaries of what we know about the universe. As we continue to explore the mysteries of the quantum world, we are reminded that Planck's legacy is far from over. It is only just beginning. Max Planck's introduction of energy quanta in 1900, which is widely regarded as one of the most significant turning points in the history of physics, forever changed our understanding of the universe. Before Planck's work, the concept of energy was widely accepted as a continuous entity, capable of being divided and transformed into infinitely smaller quantities. This classical view of energy made sense in many situations, but when it came to the radiation emitted by hot objects, it didn't add up. Classical physics could not explain the observed behavior of blackbody radiation emitted by an idealized object that absorbs all radiation that falls on it. In particular, classical physics predicted that black bodies would emit infinite amounts of energy at short wavelengths, an outcome known as the ultraviolet catastrophe. But experiments showed that this was not the case. Planck's breakthrough theory on energy quantization provided the key to solving this paradox, setting the stage for the development of quantum mechanics. Planck's quantum hypothesis was grounded in a single, elegant concept: energy is not emitted or absorbed continuously, as had long been assumed, but instead in discrete packets, or quanta. His insight was that the energy of a system could only change by amounts that were integral multiples of a fundamental unit, which later became known as the Planck constant. The beauty of Planck's theory was that it could explain the spectral distribution of radiation from black bodies without leading to the ultraviolet catastrophe. The equation he derived fit the experimental data perfectly, and it quickly became clear that Planck had discovered something profound, a completely new way of understanding the interaction between matter and radiation. At the time, Planck did not fully appreciate the scale of the revolution he had set in motion. He initially viewed his quantization of energy as a mathematical trick, a device to resolve the specific problem of blackbody radiation. However, the implications of his work were far-reaching, and in the years that followed, his ideas would reshape the entire landscape of physics. Planck's work was, in a sense, the first step in the development of a new paradigm quantum theory. Although he did not use the term quantum mechanics himself, his discovery laid the groundwork for the theory that would eventually give rise to modern physics as we know it. In the years that followed Planck's introduction of quanta, the scientific community began to embrace the idea that energy might indeed be quantized. Albert Einstein, in particular, took Planck's theory a step further with his explanation of the photoelectric effect. While Planck had introduced the concept of quantized energy in the context of radiation, Einstein applied it to light itself, showing that light could behave both as a wave and as a particle, depending on the situation. Einstein's work demonstrated that light's energy is proportional to its frequency, and that light is composed of discrete particles, or photons. This was a direct extension of Planck's idea of quantized energy, and it gave rise to the field of quantum mechanics, which would go on to challenge many of the assumptions of classical physics. Planck's theory also provided a framework for understanding the nature of energy at the atomic and molecular levels. In classical physics, the behavior of particles could be described in terms of continuous quantities, but the new quantum theory suggested that atoms and molecules could only exist in discrete energy states. This was a radical shift in thinking, one that would fundamentally change our view of matter and energy. It also raised questions about the nature of the universe itself, questions that are still being explored by physicists today. One of the key insights of quantum mechanics is that energy levels in atoms are quantized, meaning that electrons can only occupy specific energy levels around the nucleus of an atom. This realization led to the development of the Bohr model of the atom, which would become one of the cornerstones of quantum theory. For Planck, however, his work was far from finished. In the years following his initial breakthrough, he continued to refine his theories and expand on his understanding of the quantum world. Planck's work was influential not only because of the specific solutions he provided, but also because of the broader philosophical implications it raised. The idea that energy was quantized challenged the very foundation of classical physics, which had been built on the belief in a continuous, predictable universe. With the advent of quantum mechanics, physicists were forced to accept the notion that the universe at its most fundamental level is governed by probability and uncertainty, not determinism. This shift in perspective would have profound consequences, not only for physics, but for our understanding of reality itself. Max Planck's work was pivotal in shifting the focus of physics away from the deterministic worldview that had dominated classical mechanics and towards the probabilistic nature of quantum mechanics. His work provided the first mathematical evidence that energy could be quantized, and it laid the foundation for the development of quantum theory. But Planck's contributions went beyond just his scientific discoveries. His perseverance in the face of initial resistance to his ideas and his willingness to explore new realms of thought helped shape the direction of modern physics. At the heart of Planck's theory was the concept of the Planck constant, a fundamental physical constant that would come to play a central role in all subsequent developments in quantum mechanics. The Planck constant, denoted as h, is a tiny number that reflects the scale at which quantum effects become important. It is, in many ways, the key to understanding the quantum world. The value of the Planck constant is central to equations in quantum mechanics, and it has been confirmed by countless experiments. The Planck constant links energy and frequency in the equation E equals hf, where E is energy, h is the Planck constant, and f is frequency. This simple yet profound relationship formed the basis for the understanding of light and energy at the quantum level. Despite the initial resistance to Planck's theory, it quickly became clear that the concept of energy quanta was indispensable for explaining a wide range of phenomena. Planck's theory revolutionized our understanding of the microscopic world and paved the way for the development of quantum mechanics, which would eventually lead to some of the most profound discoveries in physics, including the development of quantum field theory, quantum electrodynamics, and the Standard Model of particle physics. In the decades following Planck's work, his ideas were extended and refined by a host of brilliant physicists, including Albert Einstein, Niels Bohr, and Werner Heisenberg. These scientists took Planck's concept of quantized energy and built on it, developing the full-fledged quantum theory that would change the face of science. Planck's theories became the foundation upon which the modern understanding of the atomic and subatomic world was built, and they continue to shape research in fields ranging from condensed matter physics to cosmology. The advent of quantum mechanics not only reshaped physics, but it also had profound consequences for the technological landscape. Many of the technologies we use today, from semiconductors and lasers to quantum computers, owe their existence to the principles of quantum mechanics that were first laid out by Max Planck. Quantum mechanics has also had a profound impact on fields such as chemistry, biology, and materials science, leading to new advances in medicine, electronics, and nanotechnology. In conclusion, Max Planck's introduction of the concept of energy quanta marked a watershed moment in the history of physics. His work provided the first mathematical framework for understanding the quantization of energy, and it laid the foundation for the development of quantum mechanics, a theory that would go on to revolutionize our understanding of the universe. Planck's contributions were not only pivotal in the scientific realm, but they also had a lasting impact on technology and society. Today, Max Planck is remembered as one of the greatest physicists of all time, and his legacy continues to inspire new generations of scientists to explore the mysteries of the quantum world. Max Planck's work on quantum theory stands as one of the most profound transformations in the history of science, representing a pivotal moment when the laws governing the macroscopic and microscopic worlds were radically redefined. His introduction of energy quantization in 1900 was the beginning of a new era in physics, one in which the principles of classical mechanics, which had been the dominant framework for understanding the physical world for centuries, were no longer sufficient. Planck's revolutionary insights did not just solve one particular problem in physics, the understanding of blackbody radiation, but opened the door to an entirely new domain of research that led to the development of quantum mechanics. After Planck's groundbreaking work on blackbody radiation, it quickly became evident that his hypothesis of energy quantization had far-reaching implications, far beyond the specific problem he had sought to solve. Energy quantization, a concept that energy exists in discrete units, was a radical departure from the classical understanding, which viewed energy as a continuous variable. Planck's introduction of the quantum hypothesis was not an isolated concept. It was the first step toward understanding a reality far more complex than the deterministic world envisioned by classical physics. His ideas would later be refined and expanded by scientists like Albert Einstein, Niels Bohr, and Werner Heisenberg, all of whom played crucial roles in building quantum mechanics into the theory that would describe the fundamental workings of the universe at its most microscopic scale. The notion that energy could be quantized was initially met with resistance. Planck himself struggled with the idea for years, not fully grasping its broader implications. He introduced the concept as a mathematical tool to resolve the ultraviolet catastrophe, a problem that arose in the classical theory of radiation. In classical physics, the energy radiated by a blackbody was predicted to increase infinitely as the wavelength decreased, a result that contradicted experimental observations. Planck's hypothesis, which posited that energy could only be exchanged in discrete packets, solved this problem elegantly. His formula fit experimental data perfectly, yet it was difficult for many physicists to accept that such an abstraction could represent a real physical phenomenon. To Planck, his quantum hypothesis was an expedient mathematical convenience. and it took years for him to appreciate its deeper significance. As time went on, however, Planck's ideas gained wider acceptance, and his theory formed the foundation of what would eventually become quantum mechanics. A crucial step in this acceptance came with Albert Einstein's work on the photoelectric effect in 1905. Einstein extended Planck's ideas to light, showing that light itself could behave as both a particle and a wave. This insight confirmed Planck's theory, as it was Einstein who demonstrated that light was quantized into discrete packets of energy, now known as photons. By showing that the photoelectric effect, the ejection of electrons from a material when exposed to light, could only be explained if light energy was quantized, Einstein provided empirical evidence for the existence of quanta. His work not only confirmed Planck's hypothesis, but also gave rise to the field of quantum mechanics, setting the stage for a new understanding of the microscopic world. What made Planck's discovery even more profound was its ability to challenge and eventually replace the deterministic view of the universe that had been the hallmark of classical physics. In classical mechanics, the universe was seen as a clockwork system, with every event being predictable if the initial conditions were known. This deterministic worldview was encapsulated in Newtonian physics, which governed the motion of celestial bodies, the behavior of particles, and even the interactions of light. However, the microscopic world revealed by quantum mechanics was anything but predictable. Rather than being governed by fixed, deterministic laws, the behavior of particles was governed by probabilities. The introduction of Planck's constant and the concept of quantization meant that at the atomic and subatomic level, energy and matter could only exist in specific, discrete states, and the future could not be predicted with absolute certainty. This shift from determinism to probability was the beginning of the modern understanding of quantum mechanics. Where once the universe was thought to be fully predictable, quantum mechanics introduced uncertainty into the very fabric of reality. The uncertainty principle, formulated by Werner Heisenberg in 1927, built upon Planck's ideas, showing that it was impossible to know both the position and momentum of a particle with absolute certainty. This uncertainty was not due to a limitation in measurement, but rather a fundamental feature of the quantum world. It was a realization that forever changed the way physicists viewed the universe. No longer could they rely on deterministic equations to describe every aspect of the world. Instead, they had to accept that at the quantum level, probability was the best they could offer. Max Planck's introduction of energy quanta fundamentally altered the trajectory of physics. His ideas not only provided the solution to the problem of blackbody radiation but also laid the groundwork for the development of quantum mechanics. Quantum theory would go on to describe the behavior of particles and atoms with unprecedented accuracy, leading to the development of technologies that have had an immeasurable impact on modern life, including semiconductors, lasers, and quantum computers. But more than that, Planck's work marked a paradigm shift in the way we think about reality itself. His work was not just about understanding the behavior of radiation or the interaction of light and matter. It was about understanding the nature of the universe at its most fundamental level. The quantization of energy, the idea that energy exists in discrete packets, turned out to be just the beginning of a series of discoveries that would change the course of science. Planck's ideas provided the foundation for understanding the behavior of particles at the atomic scale, and in the process, they also altered our philosophical understanding of the world. The idea that the universe is not a continuous, predictable system but rather one governed by probabilities and uncertainties challenged long-held beliefs. It forced scientists and philosophers alike to rethink the very nature of reality. The philosophical ramifications of Planck's discovery cannot be overstated. Classical physics, with its deterministic models, had provided a solid and comforting understanding of the world. But quantum mechanics, as it evolved from Planck's initial theory, suggested that the universe, at its core, is uncertain, unpredictable, and far more mysterious than anyone had previously imagined. This realization had profound implications not only for physics but for our understanding of the universe itself. No longer could the physical world be understood in terms of rigid laws and certainties. Instead, scientists had to grapple with a universe in which probabilities, uncertainties, and paradoxes became the new normal. Planck's discovery also introduced a new way of thinking about the relationship between the observer and the observed. In classical physics, the observer was an external, passive entity that measured the properties of a system without influencing it. But in quantum mechanics, the observer and the system are intimately linked. The act of observation can affect the state of the system, a concept famously illustrated by the double-slit experiment, which showed that particles could behave as both waves and particles depending on whether they were observed. This was a radical departure from classical thought, where the observer was seen as detached from the system. Max Planck's work opened the door to a new era in physics, one in which uncertainty, probability, and the strange behavior of particles became the central focus of research. His theories laid the foundation for the development of quantum mechanics, which would go on to transform not just physics, but virtually every other field of science and technology. The profound changes wrought by Planck's discovery continue to reverberate throughout the scientific community today, as researchers push the boundaries of quantum theory to explore new frontiers in technology, computing, and even our understanding of the fundamental laws of nature. In conclusion, Max Planck's quantum hypothesis was not just a solution to a specific problem in blackbody radiation, it was the first step in a new way of thinking about the physical world. By introducing the concept of energy quanta, Planck opened the door to the development of quantum mechanics, a theory that would go on to challenge many of the assumptions of classical physics and forever alter our understanding of the universe. His work continues to inspire new generations of physicists who are now exploring the strange and mysterious world of quantum mechanics to uncover the deepest secrets of nature. Planck's legacy is not just in his scientific contributions, but in the fundamental shift in thinking he brought to the world of physics, a shift that has had a lasting and transformative impact on how we understand the universe. Max Planck's contribution to the world of physics, particularly his formulation of quantum theory, changed the landscape of modern science in ways that were unimaginable before his work. One of the key aspects of Planck's revolutionary theory was its departure from the classical mechanics that dominated the scientific world at the time. Classical physics, built on the principles established by Isaac Newton, was based on the notion that the universe operated like a machine, with predictable motions governed by fixed laws. However, Planck's work would show that this was not true for all aspects of nature, particularly in the realm of the very small, the atomic, and subatomic particles that make up the building blocks of everything around us. The concept of energy quantization, introduced by Planck in 1900, was one of the earliest breakthroughs in what would later become quantum mechanics. Before this, the prevailing view was that energy could be infinitely divided, with no limit to how small those divisions could be. Planck, however, proposed that energy could only exist in discrete quantities, or quanta, and this concept would go on to form the foundation of quantum theory. The introduction of quanta, the idea that energy could only be exchanged in fixed units, was initially met with resistance, as it contradicted the classical view. But it was a revolutionary step, and over time, its significance became clear. Planck's work initially focused on solving the problem of blackbody radiation, the radiation emitted by an idealized object that absorbs all incident light. Classical theories of radiation had failed to explain why a black body emitted radiation in the manner it did, especially at higher frequencies. This issue was known as the ultraviolet catastrophe, because classical physics predicted that objects would emit infinite amounts of radiation as the wavelength shortened into the ultraviolet range. Planck's insight was that the energy of oscillators in a black body could only take certain discrete values, which meant the radiation would not increase infinitely. Instead, he formulated an equation, now known as the Planck radiation law, which accurately described the distribution of radiation across different wavelengths. This equation fit experimental data perfectly, and it marked the first time that the concept of energy quantization was applied to a physical system. Planck's introduction of quanta was not an isolated insight, but one that would be developed by later physicists, such as Albert Einstein and Niels Bohr. It was Einstein who, in 1905, used Planck's concept of quanta to explain the photoelectric effect, demonstrating that light itself was quantized and could be thought of as consisting of particles called photons. This extended Planck's work and helped further solidify the idea that energy could exist in discrete units. Meanwhile, Bohr would go on to apply Planck's ideas to atomic structure, positing that electrons in atoms occupy specific energy levels, another key concept that emerged from the quantum theory. These developments, all building on Planck's original insight, would eventually culminate in the development of quantum mechanics, a field of physics that governs the behavior of particles at the smallest scales of energy levels, far beyond the reach of classical physics. Another significant aspect of Planck's theory was the introduction of the Planck constant, a fundamental physical constant that would become one of the central pillars of quantum mechanics. The Planck constant, denoted by the symbol h, relates the energy of a photon to its frequency. It became a central constant in many of the equations of quantum mechanics, and its precise value, approximately 6.626 x 10 - 34 joule-seconds, is fundamental to understanding how the quantum world operates. Planck's constant gave quantum mechanics a concrete mathematical framework, enabling scientists to calculate the behavior of particles and radiation with incredible precision. The Planck constant's role in the energy-frequency relationship, encapsulated in the equation E equals hf, allowed quantum mechanics to describe the behavior of light, matter, and energy in ways that classical physics simply could not. The importance of Planck's work goes beyond his specific discoveries. His ideas led to the breakdown of the classical worldview that had dominated physics for centuries. Classical physics, while incredibly successful at explaining macroscopic phenomena, the movement of planets, the behavior of gases, and even the flow of electricity, could not explain the behavior of atoms and particles. Planck's quantization of energy provided a pathway for understanding the atomic and subatomic realms. It forced scientists to acknowledge that at these scales, the laws of classical physics no longer applied. Planck's quantum theory was the first crack in the classical framework, and from that point on, physics would never be the same. This shift from classical physics to quantum mechanics had profound implications not only for science but also for the philosophy of science. Classical physics had operated on the belief that the universe was predictable, that if one could measure the position and velocity of every particle in the universe, the future could be predicted with complete certainty. Planck's work, along with the developments that followed, challenged this deterministic view. Quantum mechanics introduced the idea that at the fundamental level, nature is inherently probabilistic. The behavior of subatomic particles could no longer be described with certainty. Instead, scientists could only calculate the probability of finding a particle in a particular state. This was a significant departure from the classical view, where everything could, in principle, be predicted and known. Planck's shift toward probabilistic thinking in physics laid the foundation for the uncertainty principle, which was later formalized by Werner Heisenberg in 1927. Heisenberg's uncertainty principle stated that one could not simultaneously measure both the position and the momentum of a particle with perfect accuracy. The more precisely one of these quantities was known, the less precisely the other could be determined. This principle was not due to limitations in measurement tools, as was originally believed, but a fundamental property of the universe at the quantum level. Planck's original insight into energy quantization had led to this realization that uncertainty and probability are not just limitations of human knowledge, but inherent features of the physical world itself. In the quantum world, uncertainty is not a flaw. It is a natural aspect of reality. The philosophical implications of Planck's work were just as significant as the scientific ones. For centuries, the physical world had been thought of as deterministic, a clockwork universe in which everything followed clear, predictable laws. Planck's ideas about quantization and the eventual development of quantum mechanics shattered this idea. The universe, at its most fundamental level, was not a predictable machine but an uncertain, probabilistic system. This realization had far-reaching consequences, not just for physics, but for the way people understood their place in the universe. The implications of quantum mechanics for human thought were vast, as it prompted deeper reflections on the limits of knowledge, the nature of reality, and the role of the observer in the unfolding of events. One of the major philosophical shifts that Planck's work contributed to was the challenge to the concept of absolute reality. Classical physics had allowed scientists to think of the universe as an objective, external reality that could be understood and predicted by the laws of physics. However, the advent of quantum mechanics, with its emphasis on uncertainty and probability, suggested that reality itself might be more subjective than previously imagined. In the quantum realm, the act of observation could influence the system being observed, a concept that was dramatically illustrated by the double-slit experiment. This experiment showed that particles could behave like both waves and particles, depending on whether they were being observed. The very act of measurement, it seemed, had an effect on the outcome of the experiment. For Planck, however, the philosophical implications of his work were secondary to the scientific challenges he faced. His drive was to understand the fundamental principles that governed the physical world. Yet, in the course of his work, he unknowingly helped to reshape not only the field of physics, but also the way in which we think about reality. Planck's quiet determination to uncover the hidden mechanisms of nature led to one of the most profound scientific revolutions of all time. As quantum mechanics took shape in the years following Planck's work, his ideas influenced not only the course of physics but also the development of technology. Quantum mechanics gave rise to the creation of technologies such as semiconductors, lasers, and computers, which have transformed modern society. The very devices we rely on every day, from smartphones to medical imaging equipment, owe their existence to the insights that Planck and his colleagues made into the behavior of particles and energy at the smallest scales. In conclusion, Max Planck's revolutionary work on energy quantization fundamentally altered the trajectory of physics, reshaping both the scientific understanding of the universe and the way we view reality itself. His contributions set the stage for the development of quantum mechanics, which would go on to influence countless fields of science and technology. Planck's theories marked the beginning of a new era in physics, one in which the deterministic laws of classical mechanics were replaced by the probabilistic, uncertain nature of quantum mechanics. His work not only broke new ground in science, but also introduced a new way of thinking about the world, challenging our understanding of reality and our place within it. Max Planck's legacy is not just in the equations he derived or the discoveries he made, but in the profound shift in thought that his work sparked, which continues to shape our understanding of the universe today. Max Planck's work in quantum theory remains one of the most transformative and groundbreaking contributions to the field of physics. His introduction of energy quantization in 1900, initially a tool to address a specific scientific problem, would go on to challenge the very foundation of classical physics, leading to the birth of quantum mechanics. This revolutionary shift in thinking would not only provide solutions to previously intractable problems, but would also reshape our understanding of the physical universe in profound ways. One of Planck's most significant contributions came through his solution to the blackbody radiation problem. Before Planck's intervention, classical physics, rooted in Newtonian mechanics, had been unable to explain the observed radiation emitted by black bodies. Classical theory predicted that as the temperature of a black body increased, it would emit an infinite amount of energy at shorter wavelengths, an outcome known as the ultraviolet catastrophe. This predicted outcome contradicted experimental observations, where the intensity of radiation emitted by a black body did not increase infinitely but followed a specific pattern. The inability of classical physics to explain this phenomenon posed a significant challenge and created a gap in the scientific understanding of radiation. It was Planck who introduced a groundbreaking solution. He proposed that the energy of oscillators inside the black body, the systems responsible for the emission of radiation, could only take on certain discrete values, known as quanta. This hypothesis was not just a mathematical trick, but a revolutionary concept that challenged the classical idea of energy being continuous. The energy, Planck suggested, was quantized, existing only in fixed, indivisible packets. This concept of energy quanta, which was an audacious departure from classical thought, became the cornerstone of quantum theory. The mathematical formulation Planck developed accurately described the observed black body radiation spectrum, making it a breakthrough in theoretical physics. However, what was initially conceived as a temporary fix, a mathematical device to resolve a specific problem in thermodynamics, turned out to be much more. Planck's discovery had far-reaching implications, which would not be fully understood until years later. His work laid the foundation for the future development of quantum mechanics. While Planck himself initially regarded his theory as a provisional solution, later developments in physics, particularly the work of Albert Einstein, Niels Bohr, and others, would reveal the deeper significance of Planck's insights. Einstein extended Planck's theory of energy quantization to explain the photoelectric effect, showing that light could also be thought of as quantized in discrete packets known as photons. This idea, in turn, helped lay the groundwork for the development of the dual nature of light as both a particle and a wave, a concept that would become central to the emerging quantum theory. The introduction of Planck's constant, symbolized by the letter h, was a crucial step in the development of quantum mechanics. The Planck constant, which relates the energy of a photon to its frequency, became one of the most important constants in physics. The value of Planck's constant, approximately 6.626 × 10⁻34 joule-seconds, is fundamental to many equations in quantum mechanics, such as the famous equation E = hf, where E is the energy of a photon, h is Planck's constant, and f is the frequency of the photon. This simple but profound relationship is key to understanding the behavior of photons and all forms of electromagnetic radiation. It allowed scientists to calculate the behavior of particles and radiation with remarkable precision, an ability that classical physics had never been able to provide. In addition to its scientific significance, Planck's work also brought about a philosophical revolution. Classical physics had been built upon the idea that the universe followed fixed, predictable laws. The Newtonian model, for example, viewed the universe as a well-ordered machine in which every event was determined by previous events. If one could measure the position and velocity of every particle in the universe, one could theoretically predict the future with complete certainty. Planck's theory, however, introduced a radical departure from this deterministic worldview. Energy, he showed, did not flow continuously but instead existed in discrete packets. This realization marked the beginning of a shift in physics from determinism to probabilistic thinking. The philosophical implications of this shift were immense. In quantum mechanics, the behavior of particles could no longer be predicted with absolute certainty. Instead, scientists had to rely on probabilities to describe the position, momentum, and other properties of particles. This uncertainty principle, which was formalized by Werner Heisenberg in 1927, suggested that certain pairs of properties such as position and momentum could not be simultaneously measured with complete accuracy. The more precisely one property was measured, the less precisely the other could be known. This was not a limitation of measurement techniques, but a fundamental feature of nature itself. The idea that the universe at its core was governed by probabilities and uncertainties rather than deterministic laws was a profound and unsettling realization. The introduction of quantum mechanics marked the end of the classical era of physics and the beginning of a new paradigm. Classical physics, with its reliance on determinism, was no longer sufficient to explain the behavior of matter at the atomic and subatomic levels. Planck's work and the subsequent developments in quantum mechanics provided the necessary framework to describe the strange, counterintuitive behavior of particles at these scales. The quantum world was not governed by fixed, predictable laws but by probabilities, uncertainties, and wave-particle duality. Max Planck's work did not just reshape physics, it had far-reaching consequences for other fields of science and technology. Quantum theory would go on to provide the foundation for the development of technologies that have transformed the modern world. Semiconductors, lasers, magnetic resonance imaging, MRI, and many other technologies rely on the principles of quantum mechanics. These technologies have revolutionized communication, medicine, and computing. The rise of quantum computing, a field that promises to radically change the way we process information, is directly tied to Planck's early insights into energy quantization. Yet, despite his monumental contributions, Planck was not driven by a desire for fame or recognition. He was, by all accounts, a deeply humble and introspective man. His focus was always on the science itself, rather than the accolades that followed. He was dedicated to understanding the fundamental principles of nature and was willing to challenge established ideas to do so. Even after receiving the Nobel Prize in Physics in 1918 for his work on quantum theory, Planck remained modest, emphasizing the collective nature of scientific progress. He was keenly aware that his work was part of a larger scientific endeavor and that the contributions of others, including Einstein, Bohr, and Heisenberg, were just as important in the development of quantum theory. Planck's legacy, then, is not only in his scientific discoveries, but also in his role as a guiding figure in the development of modern physics. He was the one who set the stage for the quantum revolution, laying the groundwork for the physicists who would follow in his footsteps. His work, and the ideas that emerged from it, continue to shape the way we understand the universe. Quantum mechanics, which Planck helped create, has become the dominant framework for describing the behavior of particles at the smallest scales of energy levels. It is a theory that continues to evolve, with new discoveries and insights pushing the boundaries of our understanding. Planck's influence extends beyond the realm of physics. His work challenged long-held assumptions about the nature of reality, forcing us to rethink our place in the universe. The probabilistic nature of quantum mechanics, and the idea that the act of observation plays a role in the outcome of experiments, has raised deep philosophical questions about the nature of knowledge, reality, and existence. Quantum mechanics has become not just a scientific theory, but a new way of thinking about the world, one that embraces uncertainty and the unknown. In conclusion, Max Planck's contributions to science and philosophy have had a lasting impact on our understanding of the universe. His introduction of the concept of energy quanta laid the foundation for quantum mechanics, a theory that would reshape physics and provide the framework for many of the technologies that define the modern world. Planck's work also introduced a new way of thinking about reality, one in which uncertainty and probability play a central role. His legacy is not just in the equations he derived or the discoveries he made, but in the profound shift in thought that his work sparked. Max Planck's contributions to science are a testament to the power of curiosity, persistence, and intellectual courage, and they continue to inspire scientists and thinkers to this day. Max Planck's impact on physics is monumental, particularly through his introduction of the quantum hypothesis, which completely transformed our understanding of energy, light, and matter. Before Planck, physics was dominated by classical mechanics, a deterministic system that could predict the behavior of objects with precision. However, when scientists began studying phenomena at the atomic and subatomic levels, classical physics failed to provide explanations. Planck's breakthrough in 1900, when he proposed that energy is emitted in discrete units, or quanta, changed everything. This was a radical departure from the classical view that energy could vary continuously. Planck's discovery laid the foundation for the quantum theory, which today governs much of modern physics. The development of the quantum hypothesis stemmed from Planck's work on blackbody radiation. Scientists had long been puzzled by the problem of radiation emitted by an idealized object called a black body, which absorbs all radiation that strikes it. Classical physics predicted that, as the temperature of the object increased, it would emit an infinite amount of radiation at higher frequencies. This paradox, known as the ultraviolet catastrophe, contradicted experimental observations, which showed a much more limited and specific pattern of radiation. Planck, in his search for a solution, introduced the concept of quantized energy levels for the oscillators within the black body. His mathematical formulation of the radiation spectrum accurately matched experimental data, thereby solving the ultraviolet catastrophe and giving birth to the quantum theory. Planck's work was groundbreaking not only because it solved a specific problem in thermodynamics, but because it introduced the concept of discrete energy levels, something that classical physics could not accommodate. The quantization of energy was so revolutionary that even Planck himself initially viewed it as a temporary fix to resolve a specific issue. It was only later, when scientists such as Albert Einstein and Niels Bohr expanded on Planck's theory, that the true significance of his discovery became clear. Einstein extended Planck's concept by showing that light itself, much like energy, could be quantized into particles called photons. This work was pivotal in the development of the wave-particle duality of light, which became a cornerstone of quantum mechanics. Another key aspect of Planck's legacy was his introduction of the Planck constant, a fundamental physical constant that became central to the theory of quantum mechanics. This constant, symbolized as He, is used to relate the energy of a photon to its frequency. The Planck constant plays an essential role in equations such as the famous E equals hf, where E is the energy of a photon, hf is the Planck constant, and f is the frequency of the photon. Planck's constant is incredibly small, with a value of approximately 6.626 x 10⁻34 joule-seconds, reflecting the minute scale at which quantum effects become significant. The discovery of this constant provided a concrete and measurable foundation for quantum theory, enabling scientists to calculate the behavior of particles and radiation with precision. Finally, Planck's work was not just about scientific discovery, but also about reshaping the philosophical understanding of the universe. Classical physics had operated under the assumption that the universe was a deterministic system where the future could be predicted if the initial conditions were known. This view aligned with Newtonian mechanics, which governed the behavior of large objects and celestial bodies. However, Planck's quantum theory signaled a shift toward uncertainty and probability at the atomic scale. In quantum mechanics, it is not possible to predict the exact behavior of particles. Instead, scientists can only calculate the probability of a particle being in a particular state. This shift from certainty to probability fundamentally altered the way we understand the nature of reality. Quantum mechanics, as it developed, introduced ideas of uncertainty, wave-particle duality, and the role of observation in determining outcomes, all of which broke from the deterministic, clockwork universe that classical physics had envisioned. Through these contributions, Max Planck's work did not just resolve one particular scientific problem. It changed the course of physics and expanded the boundaries of human knowledge. His discovery of energy quantization set the stage for the quantum revolution, leading to numerous breakthroughs in science and technology, from the development of semiconductors and lasers to the emerging field of quantum computing. His work continues to influence the field of physics, shaping the way we understand the fundamental nature of the universe and inspiring new generations of physicists to explore the quantum realm. Planck's legacy is not just in the equations he derived, but in the deep, philosophical shift he catalyzed in how we understand the world around us. Max Planck's contributions to science, particularly through his formulation of quantum theory, stand as a profound revolution in the way humanity understands the universe. Prior to Planck's work, the world of physics was dominated by classical mechanics, a deterministic model that could predict the behavior of macroscopic objects with great precision. Classical physics, grounded in the ideas of Isaac Newton, was based on the assumption that energy and matter followed continuous, predictable laws. However, as scientists began to investigate phenomena at the atomic and subatomic levels, it became clear that classical physics could not explain certain behaviors, particularly when dealing with radiation. Planck's groundbreaking insights into the nature of energy provided the missing piece in this puzzle and set the stage for what would later become quantum mechanics. The key moment in Planck's career came in 1900 when he sought to solve the long-standing problem of blackbody radiation. Blackbody radiation refers to the type of radiation emitted by an idealized object that absorbs all radiation that falls on it. Classical physics predicted that as the temperature of a blackbody increased, the intensity of radiation emitted would increase indefinitely, leading to what became known as the ultraviolet catastrophe. This was in direct contradiction to experimental data, which showed that radiation intensity did not increase infinitely, but followed a specific curve. In an effort to resolve this paradox, Planck introduced the idea that energy could only be emitted or absorbed in discrete quantities, rather than being continuous. He proposed that energy levels within the system of oscillators in a black body could only take specific, quantized values. This insight provided the solution to the ultraviolet catastrophe and became the cornerstone of quantum theory. Planck's concept of energy quanta was revolutionary. Prior to his work, the prevailing view was that energy could vary continuously, with no limit to how small those divisions could be. Planck, however, showed that energy existed in specific packets, or quanta, and this realization challenged the established views of physics. His work was initially met with some skepticism, as it fundamentally contradicted the classical idea of continuous energy. Despite this, Planck's quantization theory provided the first accurate explanation of blackbody radiation, and over time, it became clear that the concept of quanta would be a central pillar in the development of quantum mechanics. In addition to introducing the idea of energy quanta, Planck's work also led to the discovery of the Planck constant, a fundamental constant in physics that remains central to quantum theory today. The Planck constant, denoted by the symbol h, relates the energy of a photon to its frequency and is a key component of the equation E equals hf, where E is the energy of a photon, h is the Planck constant, and f is the frequency of the radiation. The value of the Planck constant, approximately 6.626 x 10 - 34 joule-seconds, is crucial for describing the relationship between energy and frequency at the quantum level. This constant provided a concrete mathematical framework for quantum mechanics and helped establish the precision with which scientists could study the behavior of particles and radiation at microscopic scales. Perhaps one of the most profound aspects of Planck's work was its philosophical implications. Classical physics had long operated under the assumption that the universe was governed by deterministic laws. If one could know the position and velocity of every particle in the universe, one could predict future events with complete certainty. However, Planck's quantum theory signaled a departure from this deterministic view, introducing the idea that at the atomic and subatomic levels, the universe operates probabilistically Rather than being able to predict the exact position or velocity of a particle, scientists could only calculate the likelihood of finding a particle in a particular state. This probabilistic nature of quantum mechanics fundamentally changed the way scientists and philosophers thought about the universe, raising questions about the limits of knowledge and the role of observation in shaping reality. The development of quantum mechanics, which Planck helped initiate, had far-reaching consequences, not only for physics, but for technology and society. Planck's theories led to the creation of a wide range of technologies that have transformed the modern world, including semiconductors, lasers, and MRI machines. The field of quantum computing, which promises to revolutionize information processing, also owes its origins to Planck's early work. Quantum mechanics has also had a profound impact on other fields of science, including chemistry, materials science, and biology. In many ways, Planck's contributions set the stage for the technological and scientific advancements of the 20th and 21st centuries, and his work continues to inspire new breakthroughs in science and technology. Max Planck's legacy is not just in the scientific concepts he introduced, but also in the way his work reshaped our understanding of the physical world. His quantum hypothesis, though initially met with skepticism, paved the way for one of the most significant revolutions in the history of science. Planck's work also opened up new philosophical questions about the nature of reality and our place in the universe. The shift from a deterministic to a probabilistic understanding of the universe has had profound implications for both physics and philosophy, and the concepts of quantum mechanics continue to shape the way we think about everything from the behavior of particles to the fabric of the cosmos itself. Max Planck's contributions stand as a testament to the power of intellectual curiosity and scientific innovation, and his legacy will continue to influence generations of scientists for years to come. Max Planck's work in the development of quantum theory represents one of the most revolutionary changes in the history of science. Before his breakthroughs, the universe was largely understood through the lens of classical mechanics, a deterministic view where all natural phenomena could, in theory, be predicted if the initial conditions were known. This classical perspective had been successful in explaining the behavior of macroscopic objects, such as planets and mechanical systems, but it failed when applied to the atomic and subatomic scales. It was here that Planck's work proved to be a game changer, offering a new and radically different way of understanding the behavior of energy and matter. The catalyst for Planck's groundbreaking work came in 1900, when he was tasked with solving a persistent problem in thermodynamics, specifically the issue of blackbody radiation. A blackbody is a theoretical object that absorbs all radiation that hits it, and when it is heated, it emits radiation. Classical physics, based on the laws of thermodynamics, predicted that the intensity of this radiation would increase indefinitely as the wavelength of the emitted radiation became shorter, a phenomenon known as the ultraviolet catastrophe. This prediction did not match experimental results, which showed that radiation intensity had a much more specific distribution. Planck, in an attempt to resolve this discrepancy, proposed that energy could not be emitted or absorbed continuously, as classical physics suggested, but only in discrete amounts, which he called quanta. Planck's radical idea of quantized energy fundamentally challenged the long-established view that energy was a continuous variable. He introduced the concept of energy quanta to explain the emission of radiation by black bodies. His formula, which accurately described the spectrum of black body radiation, was based on the assumption that the energy of oscillators in the walls of the black body could only take certain discrete values. This was the first suggestion that energy came in quantized units rather than existing as a continuous flow. Though Planck initially viewed this concept as a mathematical tool, his formulation was the beginning of quantum mechanics, a theory that would go on to revolutionize the way we understand the universe at its most fundamental level. The implications of Planck's discovery were far-reaching. It was the first concrete step in what would later become the field of quantum mechanics, but it also signaled a shift in the philosophical approach to understanding the physical world. Classical physics had been built on the idea of a deterministic universe, a world in which if you knew the current state of a system, you could predict its future state with absolute certainty. However, Planck's quantum hypothesis, by introducing the concept of discrete energy levels, pointed to a more probabilistic universe. This was a monumental departure from classical physics, where laws of motion and energy were predictable and continuous. The idea that energy could be quantized laid the groundwork for the later development of the uncertainty principle, formulated by Werner Heisenberg, which would establish that at the quantum level, there are inherent limits to how much we can know about a system's state. One of the most important outcomes of Planck's work was the introduction of the Planck constant, denoted as h. This constant, which relates the energy of a photon to its frequency, would become one of the most significant numbers in modern physics. The value of Planck's constant, approximately 6.626 x 10 - 34 joules-seconds, is extremely small, reflecting the fact that quantum effects become significant only at the atomic and subatomic scales. The Planck constant is central to numerous equations in quantum mechanics, including the famous equation E equals hf, where E is the energy of a photon, h is the Planck constant, and f is the frequency of the photon. This equation helps to bridge the gap between the wave-like and particle-like nature of light, a phenomenon that would become known as wave-particle duality. Planck's work did not only influence the field of physics, it also helped to spark a broader philosophical and scientific revolution. Classical physics, which had served as the cornerstone of scientific understanding for centuries, was increasingly shown to be inadequate for explaining the behavior of subatomic particles. Quantum mechanics, emerging from Planck's theory, provided a framework in which these particles could be understood as existing in discrete states. This opened up a whole new way of thinking about reality itself. In the quantum world, uncertainty, probability, and the fundamental role of the observer in the measurement process became central tenets, challenging the classical view that reality was objective, independent, and fully deterministic. Finally, Planck's work laid the foundation for the developments in quantum mechanics that followed, which would go on to shape modern physics. His ideas were expanded upon by some of the greatest minds of the 20th century, including Albert Einstein, who applied Planck's work on quanta to explain the photoelectric effect, and Niels Bohr, who used the concept of quantized energy levels to explain the structure of the atom. These developments eventually led to the formulation of quantum electrodynamics, quantum field theory, and the Standard Model of particle physics. The field of quantum mechanics has since influenced a wide range of disciplines, from chemistry and material science to biology and computer science, and it continues to be a critical area of research. Max Planck's contributions were not just theoretical, they were deeply philosophical as well. By introducing the idea that energy exists in quantized units, Planck opened the door to a new era of scientific discovery, one in which the universe is understood not through deterministic equations, but through the probabilistic behavior of particles at the quantum level. This shift from the classical view of a predictable, machine-like universe to a quantum reality governed by uncertainty and probability was one of the most profound changes in human thought. Planck's work continues to influence not just the scientific community, but our broader understanding of the universe and our place within it. His legacy is one of intellectual courage, as he dared to challenge the long-established views and offered a new perspective that would forever change the course of science. Max Planck, a name synonymous with quantum mechanics, revolutionized our understanding of the physical world. His work on the theory of energy quanta was the foundational breakthrough that led to the development of quantum theory. Before Planck's pioneering ideas, The classical view of physics was based on the belief that energy and matter behaved in a continuous, predictable manner. Classical mechanics, stemming from Newton's laws, governed the behavior of large objects, but it failed when applied to atomic and subatomic particles. Planck's contributions in the early 20th century shifted the paradigm from classical determinism to quantum uncertainty, laying the groundwork for modern physics. In 1900, Planck set out to solve the problem of blackbody radiation, a phenomenon that classical physics could not explain. A black body absorbs all radiation that falls on it and re-emits energy. Classical theory predicted that at shorter wavelengths, radiation would increase without bound, an outcome known as the ultraviolet catastrophe. This prediction contradicted experimental data, which showed that the intensity of radiation from a black body did not increase infinitely but followed a specific curve. Planck, seeking a solution, introduced the concept of energy quanta, which proposed that energy could only be emitted or absorbed in discrete units rather than continuously. This radical hypothesis was the first step in the development of quantum theory, marking the beginning of a new era in physics. Planck's theory of quantized energy was groundbreaking because it departed from the classical understanding that energy was continuous. His work suggested that energy levels within the atoms of a black body could only exist in discrete amounts, which he called quanta. This concept was initially controversial, as it challenged the established norms of physics. Nonetheless, Planck's mathematical formulation of the radiation spectrum, based on energy quanta, perfectly matched experimental observations. This achievement not only solved the blackbody radiation problem but also opened the door to a new way of thinking about energy and matter, one that would later be expanded upon by other physicists, including Albert Einstein and Niels Bohr. Planck's work led to the introduction of the Planck constant, a fundamental physical constant that would become central to quantum mechanics. The Planck constant, denoted as HA, relates the energy of a photon to its frequency, and it is a key component in the equation E equals hf, where E is the energy, h is the Planck constant, and f is the frequency of the photon. This constant is crucial for understanding the behavior of photons and all forms of electromagnetic radiation. The Planck constant became a central element of quantum mechanics, providing a precise mathematical framework to calculate the behavior of particles and radiation at the quantum level. The small value of Planck's constant, approximately 6.626 x 10, negative 34 joule-seconds, underscores the fact that quantum effects only become significant at atomic and subatomic scales. Planck's theory, while initially met with skepticism, laid the groundwork for the broader quantum revolution. It inspired other physicists to develop their own theories, expanding and refining the concept of quantization. Albert Einstein, in particular, built on Planck's work when he explained the photoelectric effect in 1905, demonstrating that light, which was previously thought of as purely a wave, also had particle-like properties. This dual nature of light, as both a wave and a particle, was one of the cornerstones of quantum mechanics. Niels Bohr also applied Planck's concept of quantized energy levels to the structure of the atom, leading to the development of the Bohr model, which explained the discrete energy levels of electrons within atoms. Another profound aspect of Planck's work was the shift it brought to the philosophical underpinnings of science. Classical physics had been built on a deterministic view of the universe, where the future was entirely predictable if one knew the initial conditions of a system. Planck's introduction of quantized energy fundamentally challenged this deterministic view. The concept that energy levels could only exist in discrete units hinted at a probabilistic universe, where particles did not follow definite trajectories, but instead existed in states of probability. This marked the beginning of quantum mechanics, where the uncertainty of particle behavior became an inherent part of the theory. It was a concept that would later be formalized by Werner Heisenberg in his uncertainty principle, showing that it was impossible to simultaneously measure both the position and momentum of a particle with complete precision. Planck's work, although initially isolated to the realm of theoretical physics, would go on to have a profound impact on technology and industry. Quantum mechanics, the field that grew out of Planck's ideas, became the foundation for technologies that have radically transformed the world. The advent of semiconductors, lasers, and the technology behind magnetic resonance imaging, MRI, machines all owe their origins to the principles of quantum mechanics. More recently, the potential for quantum computing, a technology that promises to revolutionize the way we process information, is based on the very concepts first introduced by Planck and his contemporaries. Quantum technologies are shaping the future of computing, communication, and medicine, making Planck's contributions not just of historical interest but of current and future importance. Planck's legacy in the development of quantum mechanics also brought a deep philosophical reflection on the nature of reality itself. Classical physics had depicted a universe governed by clear, predictable laws. With the advent of quantum mechanics, that view was shattered, replaced by a probabilistic model where certainty was replaced by uncertainty, and measurement played a central role in determining outcomes. Quantum mechanics revealed that reality at the microscopic level was not deterministic but probabilistic, a concept that challenged not only the scientific community but also our broader philosophical understanding of the universe. The implications of quantum theory have permeated into discussions in philosophy, particularly with regards to the nature of existence, knowledge, and reality. Max Planck's work, though initially isolated in scope, would go on to shape not just the course of physics, but the course of human thought itself. His introduction of energy quantization, the Planck constant, and his contributions to quantum theory provided the foundation for some of the most important scientific advancements in history. The philosophy of quantum mechanics, with its focus on uncertainty and probability, remains one of the most profound changes in the way we understand the universe. The impact of Planck's work continues to reverberate throughout modern science and technology, and his legacy as the father of quantum mechanics remains as important as ever in the ongoing exploration of the fundamental nature of reality.